Hi, my name is Joel Segrin. I'm Fantech's National MVHR Solutions Engineer, and I'm here today in the Fantech workshop to step you through HVAC, new integrated products. So we're going to talk a little bit about MVHR essentially and what products have arrived to help you with heating, cooling, dehumidification, and just a few concepts to hopefully further advance some understanding in this area. So we're going to step through a few areas today. We're going to talk about PHI warm climate testing update. So they've done some work to now test MVHR units for efficiency and operation under warm climates. And you'll understand the benefits of that a little bit later. We're also going to talk about MVHR integrated heating and cooling. So can we satisfy heating and cooling demand for your building just with HRV integrated solution, and the same for dehumidification, what options are here on the market and what's being used. And lastly, we're going to touch on NCC 2019, which was released not that long ago. For people not in Australia, that's our National Construction Code, so it governs the way we build and ventilate our buildings, and so it's an important part. Whilst we can maintain passive house requirements, we've got a dual obligation to also maintain our construction code requirements. So first of all, PHI warm climate unit certification. So most people are probably familiar with the certificates for MVHR units, and they cover things like airflow rates, they cover efficiency, they cover specific fan power consumption, a little bit on noise. And to date, they've really been tested for cool climates. So the standard test data has been something that's more typical of Europe or northern parts of Europe. What has been fairly evident from early on is that summertime operation is slightly different to wintertime operation in terms of efficiency. And the main thing that's contributing to that effect is actually heat dissipation from fans. And so if we have a look at this diagram at the bottom here, we can see that those round circles there are the fans in the airstream. And we find that they, under all conditions, they're actually going to contribute some heat to the airstream. So anytime we have inefficiencies in fans or motors, and that's always the case, not all electrical power is converted into mechanical power or airflow or fluid movement, we're going to get some heat dissipation. And so for cool climates, where it's typically cold outside and we're trying to bump up the indoor temps, those heat dissipation has actually aided in the effective heat recovery efficiency. But when we're now talking warm climates, that actually has a deterioration on efficiency. And so it's important as PHPP is refined and the passive house process refined that we start to identify and reduce error in some of these regions. I think that's fairly straightforward there. We'll have a look at what those certificates look like. So on our left here, the blue version is obviously the winter time one. That's probably the one you're familiar with, cool climate. You can see on the right-hand side, we've now got the red data for warm climate. Fairly logical. You'll notice that the airflow range is really not any different, but you'll notice an efficiency difference. Now, this is for the same unit. So it's a 350 cubic metre typical unit you'd use in a residential build, but you'll notice there's a 3% efficiency difference. Now, that is really just due to the fact that it's operating under some now warm outdoor air conditions. And what's happening is that heat dissipation that in the cool climate was contributing to efficiency is now actually reducing efficiency. And so you can see from our total energy balance in PHPP, the effect is not insignificant. So we really should start to compensate for that. So there will be a future release of PHPP. I don't know exactly when that is, but it will start now ask you for warm climate data as well. My understanding is there'll be perhaps dual pages, a winter and a summer page, or some calculation for efficiency in both winter and summer conditions, rather than assuming evenness across the whole spectrum. We noted here 3% efficiency difference. This is a fairly high performance unit, as you can see, with efficiencies up around 90%. Where you get into lower performance units, typically the fan power consumption will be higher and you're likely to get more heat dissipation. So whilst we can see 3% is the difference there, we'll actually find that's a fair bit greater for lower quality units. So something to pay careful attention to. Okay, so into some integrated heating and cooling solutions. I've spoken before at previous conferences about some other concepts, and I won't look to repeat those. This is really more an introduction on what's new. And so one of the newer products is actually a standalone unit. So as you can see in that diagram on the left, it's a all-in-one unit or an integrated unit. So you can see the obvious heat exchanger in there, or ERV core in this case. Typically you would be able to get either an enthalpy or a sensible type core, typical fans, but what we've also got in there is a cooling coil. And that could, in theory, be either a refrigerant type, so DX type operation, a bit like your split system air conditioner, or it could be chilled or hot water type coil, whereby you're using some external source to provide hot cold water to that. Either way, we're going to deliver some heating or cooling. Now, one of the things that has always been a capacity limit for delivery of heating and cooling has been the fact that the airflow of the HRV unit has really dictated the amount of capacity for heating or cooling. And it's typically for a 350 cubic metre per hour unit, which is about 100 litres a second. The capacity has really been sort of 2 to maybe 3 kilowatts tops on heating. And that has been a little challenging in most projects, even certifiable passive houses. It tends to be fairly marginal. It is potentially what you see highlighted in PHPP as your heating cooling load, but noting if we just match that, we're really going to get something that's great in steady state operation. But what we've found through experience is the recovery if you let the indoor temps run away. And the classic example has been someone goes away, doesn't close any blinds, doesn't do any purge cooling at night, and the building overheats a bit. They come home, put their integrated cooling on, and it takes a long time to try and get that temperature down. And that could be many hours. It could be 6, 8, 10, 12 hours, which for a certain proportion, a reasonable proportion of people, is unacceptably long. So the aim has always been to try and boost that heating cooling capacity. Now, what has been stumbled upon or evolved is the idea of having a recirculation loop. And if we look down in the bottom left-hand corner, you can see where I've drawn the blue line. So as well as air coming in the outdoor or ODA port on that unit and through the unit, we're also supplying some air that's been heated or cooled into a living area, and that has a recirculation loop. So now the airflow across the coil, the heating cooling coils, can be roughly double what it was, because it's no longer just related to the exact HRV airflow capacity. So hopefully that makes some sense, and we can sort of get now more like 4 kilowatts up in that sort of area, heating and cooling, which starts to make the application a little bit broader. The other benefit of this type of unit is it's all in one, so the controls and everything are integrated. As you can see in the top right-hand corner there are a couple of options, as we mentioned, air source or water source, heating, cooling source. What you choose there is really up to you. Certainly, DX type products are typically a fair bit cheaper than water at the moment, and probably will continue to be, so that can be a fairly sensible choice. Also makes the piping fairly simple, but an interesting product. Typically these products are not at the upper end in terms of heat recovery efficiency. So the unit is an all-in-one, designed to be multifunctional. Obviously with heating and cooling, the efficiency for a broad application becomes slightly less critical. But in the passive house market, equally, we're still looking ideally to get really high heat recovery efficiencies. So that said, some of these units, there's a couple I'm aware of that have actually reached pH certification standards, and they've got efficiencies for heat recovery in the order of 78%, which, as I said, is not at the upper end of the scale, given the better ones are approaching sort of 90% heat recovery efficiency, but they are a compact solution. What I would say is that there are plenty of imitation units in certainly in international markets. By imitation, I mean have similar components, but not anywhere near passive house certifiable standard. So air leakage, for example, could be fairly poor, or case insulation. And so when you see that sort of product on the market, and it's not particularly common just yet, but I expect in the next couple of years we'll see more of that. It's going to be important that you look for test data, and I'd suggest pH certified product is still a much safer way to proceed. The other component we've got there for integrated heating and cooling, and this is not particularly new, but it's just a slightly different concept on an old idea, is coil boxes. And so these are post heating or cooling. Post meaning you've had your outside air, it's come down through your MVHR unit, you've recovered as much heat or cool as you can, and you need to do a little bit more cooling or heating. So these particular units are designed to integrate fairly seamlessly to the manifolds. So there's no sort of messing around with ductwork. They are chilled water. I've not seen a DX version at this point in time. They are sort of 100% MVHR airflow, so the capacities are limited. We talked about sort of 2 to 3 kilowatt type capacities at that 350 cubic metre per hour flow rate. You can see this one's got a sloped coil. What that does is allow the manufacturer to maximise the surface area, so we can get capacities up a little and we can get pressure drop, so coil pressure drop down, which is important because you've got airflow running over that coil every day of the year, even when it's not in use, so it needs to be designed such that pressure drop's pretty low, i.e. you haven't got overhead fan power consumption that's horrendous. Hot water supply for these is fairly simple because we've got domestic hot water obviously, but the challenge at this point is chilled water for that sort of product. Now reversible heat pumps are available in the market, but they're still fairly expensive, and it's, I guess, unclear whether they're going to fall much in price given time, but a little bit of market research has suggested that you're probably looking at anywhere from $6,000 to $9,000 for a reversible heat pump that could give you chilled or hot water. And it's interesting to note that those capacities there are really at the low end of reversible chillers. So most of that product in the market is a commercial type product. It might be a little bit noisy, so that's the other thing, because it's been destined for a plant room rather than outside your bedroom window. So it's just a little bit of care needed there. and some evaluation of cost, whether that sort of makes sense for you. If we look at dehumidification options now in humid climates, we've got quite a few different concepts there, and I'll step through some of those. So portable dehumidifiers, they're obviously relatively cheap and readily available. The downside is they are single room, and if they're portable, they're capturing water. At some point, you've got to stop and discharge that water. Split system ACs. Now, you're probably aware that whenever they're cooling, they're also dehumidifying. So that is an option. They provide heating and cooling, so that's a good part of that option. The cons are in a split system format, they're really a single room and they must cool and dehumidify together. You can't separate those independently. We'll touch more on that. MVHR integrated, so what's possible there? The pros there are you get whole house coverage through your duct system, but you've got some limits again, like heating and cooling based on airflow. And ERV core, so moisture exchange. We'll sort of explain why that's going to need some assistive technology, meaning you're going to need some other form of dehumidification. It's just going to assist you. So why not just use the split system AC? Now, we'll have a little look at what's called a psychrometric chart here to explain what comfort is, but intrinsically we all know comfort is a mix of both temperature and humidity. We've all been to Queensland or somewhere tropical, and whilst the temperature's been lovely, it's been a bit stuffy and sticky. And so that's sort of what we're talking about. The concept of an air conditioner SHR value or sensible heat ratio. And the next slide will give you a little bit of an idea of what that is. Doesn't often match what we need in high performance houses for more humid climates. And we're talking definitely Queensland here. We might be talking northern New South Wales, just depending on your specific locations. So as I mentioned, this is a psychrometric chart. It's a bit of a nerd's dream, but the important parts really are to understand that across the bottom we've got dry bulb temp, or temperature that we feel, and up the top, up the left-hand side, or the vertical axis, we've got humidity ratio. So we're really talking about how much moisture is in the air. And if you look at the sort of sweeping lines on that, you can see them marked off at 20, 30, 40%. They're lines of relative humidity. So that might make some sense. And really what we've tried to explain here is that these air conditioners that are mass produced have fixed ratios of heating, fixed ratios of cooling and dehumidification. And these are represented in the two legs. So when we have a look at the blue or the purple, and that's two different types of operation, same air conditioner, but in the light blue example, AC strategy 1, we've done a bit of cooling, and at the same time, that cooling is represented by a horizontal line going from 30 to, let's say, 24 degrees. We've also come down vertically, so we've got rid of some moisture out of the air. But the problem is we haven't ended up in our comfort band, which is that red shaded area. Now, the comfort band might sit a little bit higher than classic passive house, but different people will, in general HVAC terms, will define that according to what they want. The principles are still the same in that it's difficult for a humid starting point, and that's to the right there. So this might be a northern New South Wales or maybe even Queensland example where our summer design temp is about 31, 32, and a relative humidity a little bit above 50. So that's probably Brisbane or something like that. What we can see is using the AC unit on its own, we can cool, but we can't get the temperature and the humidity correct at the same time. So we end up right temperature, but still sticky, or too cold once the humidity is in the right area. So what can we do to solve this? Well, the first simplest part to that is ERV core, or enthalpy type cores. So what we've got here is instead of a core that's giving us only sensible or temperature exchange, we do moisture as well. And for good quality cores, we can get up to 65% efficient moisture transfer or recovery. Now, in this example, our intake air, this could be Northern New South Wales at 16 grams per kilogram. Our extract air, which is essentially what's in our building, so bottom right there, is about our passive house humidity threshold, about 12 grams per kilogram. When we extract that, we're bringing 16 grams potentially in, but the moisture recovery actually strips some of that away. So you can see top left hand, the exhaust air has now got more humidity in it than the intake air. But importantly, the supply air at 13.4 grams has actually been reduced from 16. So what's obvious here though is that we're going to accumulate moisture in the building still. We've been extracting 12 grams per kilo, but we're actually putting 13.4 in. So this requires some ancillary dehumidification as well. And we also needed some ability to get to 12 grams per kilogram to begin with. So as we've touched on, ERV cores aren't a standalone solution. They're going to need some dehumidification as well. We're going to talk about a couple of different concepts here for this dehumidification. So the first is the desiccant wheel concept. So as it sounds, it's a rotating wheel, and it's actually got some coatings on the wheel that absorb moisture out of the air. Now the concept here is we pass air through the wheel, we absorb the moisture, and then it rotates into a little sector that you can see there. And in this one, it actually has a bit of a loop. Essentially what's done is a heater is used to raise the temperature of that portion, that air flowing through that portion of the wheel. And essentially what that does is evaporates the moisture off the desiccant crystals, and it can be then discharged. So the cooler air comes, those desiccant crystals absorb the moisture for, let's say, 300 degrees of that circle, and in the other 60 degrees we reheat that air, get it up so we re-evaporate the moisture, and then we dump it. And so it's a relatively simple technology, something that's been around for a while, simple concepts, not too many moving parts by comparison to refrigerant type that we'll talk in the next slide. What we find here is we can find units that are about the right sort of size for our standard home. We find dehumidification levels around about 26 litres per day. That might not be enough still to meet your peak load for Queensland. So you need to be careful there. They do have reasonable power consumption. So this particular model that'll do 300 cubic metres per hour is about 1500 watts, so not insignificant. There's about 1000 watts of fan power, 100 watts of fan power, but that heater there, because we've got to get that air temp up on that discharge area, is about 1400 watts. So there is some reasonable power consumption. Also not particularly silent, so most of that will be fan power noise in there, so we just need to be a little bit careful about where that's positioned in relation to being a nuisance. But relatively compact, because that wheel's compact and the heater can be small, it can fit into a fairly small location. What we do suffer is a loss of some airflow out of these. So that airstream that takes away that moist air is actually lost supply air. So we're going to lose potentially up to 25% of our airflow to what they call the wet air exhaust. And if we look in the top right corner, I've sort of sketched in the wet air stream. It's not a condensate drain, so the moisture is still in gaseous form. The water's still suspended, and so we can discharge that. We could link that back into the HRV exhaust and discharge it that way. The other thing to note for this and the next solution is that both of them have fan power, permanent fan power increases. And when I say that, I mean in the MVHR fan power. If you were to install them in a sort of bypass circuit, so you had a little dog leg out so that you use some valves to only push air across your dehumidifier when you required it in summer, then you could avoid that. But if you make it an inline component that's always inline, you're going to suffer some increase in permanent operating power. If we look at the next option there, it's the refrigerant type, and this is probably classically what people have seen a little more often. It is basically the same thing as a split system, but you'll note there it's got two coils. Essentially, that type of dehumidification occurs by getting the air temp down really low, and when it's low, can't hold much moisture. That moisture falls to the bottom of that coil, and you'll note top right hand shows a condensate drain, but we then use the shaded red coil to bring the temperature back up to what it originally was. So in this instance, we can get dehumidification, but we're not getting cooling at the same time, which is what we want. 450 cubic meters per hour, there's little units around like that. You're probably $2,000 to $3,000. Lower power consumption. So we're using the same sort of compressor and refrigerant technology. So you can get COPs probably in the order of 3. Again, noisy, not hideously, but something you need to consider. And that is because you've got a compressor running in there. So the coils are silent, but that compressor is going to be the significant noise generator. They're a bit larger in size. Obviously, compressor's got to be in there, a couple of sets of coils. There's a little more going on. There's some refrigerant being pumped around. And you'd want to check what your sort of standby coil pressure drop. So how much fan power, MVHR fan power, are you going to consume running across those two coils if you have it as a permanently inline device rather than in a bypass or a dog leg type conjunction, arrangement rather. So a couple of different concepts there for dehumidification. Which one suits you is going to depend on some individual circumstances and availability of product. But the idea there was just to say, look, hey, there's a couple of different concepts there and see what works best for you. How many hours a year you think you might need to run it for. Lastly, NCC condensation management. So 2019 has seen the introduction of a condensation management section. So the idea here is to make sure that we're not getting moisture damage and health impacts from condensation that's not removed in buildings that leads to mold growth and structural damage. So it applies to class 1, 2 and 4, this specific condensation management section. And what's of significant interest for us is the section on flow rate and discharge of exhaust systems. Now, it is written in a slightly interesting manner in that it's basically saying if an exhaust system is installed, it must comply with these values, rather than being you must install an exhaust point of this rate. So, but what we find with a MVHR system is we are going to have extract points there, but we also don't want to extract anything like the volumes they're talking about there. So for example, we look at bathrooms or sanitary compartments, they're talking about minimum 25 litres per second, which is 90 cubic metres per hour. And for laundry, it's 40 litres a second or 180. Now that's obviously well above what we want to ventilate for a typical laundry or bathroom. That has the consequence of greatly increasing unit size, HRV unit size and cost. It has a dehumidification, over dehumidification risk because of the high volume of air we're now having to move through the building. It requires extra duct, larger grills, so the impact is fairly extensive and expensive. Interestingly, no duration of operation is given for these sort of what we tend to call intermittent flow rates. So there's no guidance to say if you were using that 25 litres per second that you only need to use it while you're in the bathroom. So there's a lot of interpretation done there. What we've done to address that is put together a performance solution, and it's just being finalised now as we speak. But essentially, we engaged Thermal Environmental to produce some modelling. When I say we, the Australian Passive House Association coordinated that, and this was gratefully sponsored by MVHR suppliers in Australia, so those that supply sort of premium passive house level equipment, pulled funding together to support the costs for modelling and then creation of the performance solution. But in essence, what we did was pick 8 cities across 5 climate zones, and we modelled them under both the NCC rates, those that are in the condensation section, and then also against typical passive house rates, but obviously continuous. And the NCC ones were intermittent. So we made some assumptions about how long an exhaust fan might typically run for in a bathroom. And it's typically around how long an occupant's there. No one really leaves their fan on for another few hours and comes back at morning tea to turn it off. And I've shown you just a quick snapshot there of Sydney outcomes. It's a little bit difficult to follow, but red and green are the 2 different ventilation rates there. The passive house is the green one, NCC is the red, and what we're showing on the vertical axis is relative humidity, and on the horizontal axis is the 365 days of the year. And what you can see there, the blue line at the bottom is the difference between the 2. So that's below 0, which is a good thing for us with MVHR units, because it's saying that whenever this is below that 0 line, the relative humidity under the MVHR solution is better than the NCC. And what you can see here clearly, for the vast majority of the time, in fact 91% of annual hours, we get better performance with MVHR system than we do with a standard NCC system with some reasonable assumptions about operation. On the right there, you can see a shorter term daily relative humidity. You can see the spikes there. Again, it's a difference between the 2, but you can see the spikes that relate to showers and things like that, but they rapidly are dehumidified and come back to the low levels. So in summary, there's been quite a bit of innovation continue in sort of HVAC products. These are typically being driven out of Europe, maybe to some extent in Asia, but they are taking some time to get from Europe to Australia. And that's related to complexity of product a little bit, and that might be about elect safety compliance. So any items that are considered not low voltage, so anything more than about 50 volts, is considered we'll call it high voltage or non-low voltage product. And this is for Australian markets specifically. This comment requires a fair bit of testing to make sure it's electrically safe. And also the market size, when European manufacturers are looking at distribution, typically places it a little bit behind Europe. A, they like to test their product more locally, so that any rectification is a little bit easier, but B, they'll always tend to satisfy their larger European markets before the Australian or New Zealand markets. So we'll see some of this product come through. It might take some time. What I would also say is work with your passive house consultant to determine what requirements you have for your project on heating and cooling and dehumidification. There's really not a lot of point approaching your MVHR supplier saying I need some dehumidification when we've got no way to understand what that is, because those things are very climate and the proportion of heating and cooling you need and dehumidification are very project specific, so both climate and project specific attributes. And so without that data, we really can't start to help you with products that might be suitable. So thanks for your attention. I hope we've been able to share something useful there, and look forward to talking again in the future. Bye for now.